Yeah,
I remember that.
All right, welcome everybody. Edward's away, so I get the pleasure today of introducing our speaker. My name is Mike Dietrich. I'm chair of the HPS department. A couple of announcements before I introduce Bob. Next week, Jim Tabery will be back in town on Tuesday to give a talk at noon on the Black prisoners of Statesville, race, research, and reckoning at the dawn of precision medicine. There'll be a special HPS talk Friday, October 25th at 3:30. It's in person only. The Physicist and Philosophy of Physics by Jim Peoples, a Nobel laureate in physics. That'll be downstairs in the 10-4 seminar rooms. And then next week, Mike Dietrich, whoever that is going to give a talk on Tuesday called "Does Species Diversity Matter for Biological Research?" Yeah, we'll see. And then on Friday, Alita Dewey is going to give a talk on November 1st, reformulating rational analysis. So today it's my pleasure to introduce Bob Batterman. Bob is a distinguished professor of philosophy and the current DGS in the philosophy department.
That's right. Email Bob. Everybody heard that, right?
Bob got his PhD in Michigan in 1987. Prior to arrival in Pittsburgh, he was the Rotman Canada Research Chair in Philosophy of Science at the University of Western Ontario. Before that, he spent 15 years in philosophy at Ohio State. He's a fellow of the Royal Society of Canada, author of numerous articles and books, including The Devil in the Details, Asymptotic Reasoning and Explanation, Reduction, and Emergence. His work in philosophy of physics focuses primarily upon areas of condensed matter, broadly construed. Research interests include foundations in statistical physics, dynamical systems and chaos, asymptotic reasoning, mathematical idealizations, philosophy of applied mathematics, explanation, reduction, and now deep learning as well.
Yeah, so I started to think a little bit about deep neural nets when I was advising Katie Creel's dissertation. Katie was a PhD student in HPS, and she forced me to think about this a little bit, and so I blame her. Then I wrote this book about kind of this mesoscale correlational methodology that I think people haven't paid enough attention to, and then I started to think that maybe there's some connection. So this is my attempt at telling you what the connection is. All right, so deep neural nets have been and can be, hopefully, remarkably successful, but there remain a lot of significant questions as to why. Why do they work? A number of authors have suggested or implied that one might explain some successes of deep neural nets by arguing that they are implementing in some sort of way certain renormalization group-like operations, which are kinds of a scheme for coarse graining, throwing away irrelevant details. And so what I'd like to do here is to explore and perhaps go beyond aspects of the suggestions that have been made in the literature so far. While I believe that claims of an exact mapping between deep neural nets and the renormalization group are likely overblown, certain deep neural nets can be understood as extracting relevant correlational information that's hidden in the input data. So here are a couple of broad reasons for thinking that there's at least some kind of connection between how deep neural nets work and the renormalization group. The normalization group allows one to extract information concerning continuum scale behavior, for example, the critical behavior of fluids, from all of the irrelevant gory details about the molecular makeup of those fluids. And deep neural nets seem to apparently allow one to extract information relevant to classifying an image as a dog from all of the irrelevant gory details in the pixels that make up the input image. So I want to suggest that these procedures are successful to the extent that they are, because there is genuine correlational information hidden in those gory details. And I also think that we can say something about the nature of that correlational information and where it comes from. And I can try to tell a story about how deep neural nets seem to be able to extract that information. So these correlations reflect the fact that the world exhibits various kinds of scale invariances. In particular, the correlations that are involved in these inhabit a scale in between the micro level of molecules in the context of fluids, and maybe the level of pixels in the context of images. They inhabit these scales in between, and what you would like to do is to be able to access those sort of correlational structures. And maybe this level talk here might also help to explain something about the hierarchical nature, the depth of deep neural nets, although I won't have much to say about that today. Okay, so let's talk about images. So Daniel Renormalization and Professor Bialik from Princeton University in 1994 took a bunch of photographs in a state park in New Jersey. The photos were primarily of trees, rocks, and a stream. They measured 256 by 256 pixels and corresponded to 15 degrees in visual angle. The data that they collected was the logarithm of each pixel's luminance. The data showed scaling, quote, in the power spectrum of the form given here in equation 1, with k being the spatial frequency, a is a constant representing the overall contrast power in images. And for their data, the so-called anomalous exponent, eta, had the value of 0.1. That is to say, there's a kind of power law structure to this power spectrum. So the question that I want to ask is, how can we understand this power law scale? So one could imagine forming blocks of pixels in analogy with the blocks of spins in real space renormalization schemes that Kadanoff introduced. We would then see the same statistical structure in the pixel blocked images after appropriate renormalization. So here in this picture, there are a bunch of spins on a lattice, and we group them into groups of 9, and we perform some kind of coarse graining scheme. In this case, it's a majority rules, kind of like max pooling in deep neural nets. And so we replace 9 individual spins with one single block spin, right, which reflects the correlations among the individual spins. And then in the renormalization group, one rescales, puts those big block spins on the same spatial lattice that the original spins were on, and then does some renormalization to make them look as much like the other ones as possible to actually minimize the difference in the free energy. So Renormalization and Bialik actually do this pixel blocking. They plot the contrast phi of these images, normalized to unit variance, averaged over n by n pixels for n equals 1, 2, 4, up to 32. And this plot here is a plot of all of those different blocked images, and the data all collapses onto the same non-Gaussian distribution. Okay. So another indication of the robustness of the statistical structure in natural limits is shown by trying to implement quite radical recalibrations of the data. So I could change, and Renormalization did this, change the grayscale images in the database to black and white images. That produces a new data set, but with virtually the same scaling statistics. Here's a quote from Renormalization. That the process of geological formation of hillsides and valleys, or the structure of forests due to the succession of flora, can exhibit scaling through their images is perhaps not altogether surprising. It is striking, however, that the natural image data sets in which the scaling was found are all quite different. No two sets of pictures were even from the same environment. So this is, I think, really suggestive, and it's kind of where I want to focus. So the scaling result from that equation 1, this equation here, is a function of the spatial frequency, k. And the frequency domain is not the best way to understand the properties of natural images that are responsible for scaling. In the Fourier domain, that is in this frequency domain, objects are spread out and superposed over many frequency bands. So Renorman reformulates the results in the spatial domain, and I'm skipping a bunch of details here, by introducing what he calls a pixel difference function that's going to allow him to define objects statistically. And this is one of the crucial take-home points of this talk, is that we want to try to think of objects in a statistical sense, the objects that appear in images statistically and not semantically. That's I think there's a big mistake in some of the literature, and I want to try to say something. So this pixel difference function is a kind of expected variance. Pixels in different objects are going to have a larger mean squared difference in their luminance than those that belong to the same object. Equivalently, pixels that are in the same objects are going to be more strongly correlated. So just taking that square and expanding it, Renorman shows that it takes this form here. And the values for these constants D1 and D2 were determined, this is 1990s, so without too much computer power, by selecting 10 to the 5th 100,000 pixel point pairs from the images at random and calculating their joint. They came up with numbers for D1 and D2, and that yielded a value of eta equal to 0.19 in accordance with the anomalous dimension that we saw in the power spectrum. So how can we explain this? Like, what is responsible for the form of the pixel difference function, dx? And specifically, what explains the value of the scaling exponent? So here's a simple but important observation. Each pair of pixel points from an image can either belong to the same object or to different objects. And we need to, in order to determine the statistics, we need to determine the probabilities that such point pairs are in the same object. Another important feature is that in natural images, like some objects can occlude other objects if they happen to be in front of it when you take the picture. And so Renorman constructed a simple model of image generation that allows for this occlusion, and that lets us identify statistically independent image components as objects. Thus, as I said before, objects are going to be defined statistically in this context and not semantically. So here's the model, and this is just like a great instance of somebody coming up with. So imagine walking on an infinite image plane. At a random location, you blindly select from a number of choices an infinitesimally thin cardboard cutout of some particular shape. You painted a gray tone chosen from some distribution and drop it on the ground. That done, you continue to another random location and repeat the process. So it's entirely possible that one of these cardboard things is going to occlude another. For this model, Batterman finds that there's a correlation function, C of x, where again, x is the distance between the pixel points. It's equal to C0 times P sub same, where P sub same is the probability that a given point pair separated by, it's actually angular distance x, belong to the same object, and where C0 is the constant correlation within objects. And so a power law in the correlation function, if we can find a power law in this correlation function 3 here, then that means there's a power law in the spectrum. And to show that, we need to calculate and demonstrate that P sub same is itself a power law. So how do you do it? Well, you randomly throw line segments of length x on the plane. In this case, just he chose rectangular objects, but they could be any shape. And there are 3 options, right? Either option A, neither of the 2 points separated by the distance x are in the object. Option B, one of the 2 points separated by the distance x are in the object. Or item C, probability C, is the probability that both endpoints of the line segment are in the object. And so with some calculations, we can determine the probability that they're in the same object is equal to P2 of X divided by P1 of X plus P2 of X, where we saw how to calculate those different probabilities. Batterman concludes that the scaling of interobject probability follows directly from the scaling of apparent object sizes. In images of the real world, this apparent object size in degree depends upon the object's actual size, the worldly object's actual size, and its distance from the observer. The overall distribution of apparent object sizes is a function of the distribution of the object sizes and of their distances. And building on, it's easy to see how, given work I did on this in the middle way, but right, it's easy to show that you can find higher order statistical correlations by throwing, instead of line segments or points, you can throw triangles and ask what's the probability that all three vertices of a triangle are in the same object or not, etc. Right? So this Batterman is actually introducing and employing this kind of correlational method in order to essentially kind of reconstruct a field. So in fluid dynamics, for example, and we have these parameters like the viscosity of the fluid that typically we measure and we put parameter values in, but they're really defined over a field, over the real numbers, right? And so one can reconstruct a field by looking at the various endpoint correlation functions. And for those of you who know stuff about quantum field theory, that's the same thing. So the key takeaway is that the scaling structure in natural images is a function of certain correlations between the pixel values. The power law scale invariance in natural images is a function of that correlational information. And so what I'm going to do is suggest that the effectiveness of deep neural nets in image recognition, among other tasks, depends upon the existence of that correlational information that reflects real world features. So part of what I'm doing is building on work by Jim Woodward, Porter Williams, and Holly Weinberger about what does the world have to be like? What's the worldly infrastructure have to be like in order for these deep neural nets to be successful at their job, in particular in the context of image recognition? Okay, so now let's turn to deep learning, deep and cheap learning. So in an influential paper by Lynn Techmark and Rolnick, entitled "Why Does Deep and Cheap Learning Work So Well?" they aim to show how the success of deep learning depends not only on the mathematics of neural networks, but also on certain facts about the world. The world has to be certain. Here's a puzzle that they set. How can neural networks approximate functions well in practice when the set of possible functions is exponentially larger than the set of practically possible networks? And this is an important question because even in networks which have only one hidden layer, really shallow networks, you can show mathematically that they're universal function approximators. So given a sufficient number of hidden units, any smooth function can be approximated to any arbitrary accuracy with just a single hidden layer. So Lynn et al. Give this quick estimate that demonstrates that networks of feasible size just can't do this. They say there are 2 to the 2 to the n different Boolean functions of n variables. So a network implementing a generic function in this class requires at least 2 to the n bits to describe. In other words, it requires more bits than there are atoms in the universe if n is greater than 260. So the space of all functions is enormous, but nevertheless, there are these results that say deep neural nets or shallow neural nets can calculate any one of these functions. Despite this, neural networks of feasible size, that is, actually implementable neural networks, have been extremely successful. And this paper argues that there are physics reasons, that's their term, for why scientists, physicists typically care only about certain functions. Hamiltonians that have low polynomial order, that exhibit certain asymmetries and then involve local interactions. And because these are the interests of the physicists, I'm not so sure why they're talking about physicists here, given that like we're trying to do image recognition too, and we're not writing down Hamiltonians for that. But this is from their point of view. So the kind of functions they say that we want to approximate are extremely far from being random. And the fact that they argue that one reason DNNs work so well is because the space of functions we actually care about is extremely small. It's an extremely small subspace of the space of all of the functions. So I think there's something right about that, right? But I don't think it can be the whole story. It's not much of an explanation, really. First of all, our interests can and should be only part of the reason, it seems to me, why DNNs work. And as I just said, it's not clear that we're thinking in physics terms when we're trying to train deep neural nets to recognize a certain input of pixels to be dogs or not. I talk about dogs because I have them and I don't have any cats. Of real interest, though, is how these deep neural nets actually find the functions that work, right? The functions that correctly recognize objects at the scale of dogs, given input at the scale of pixels. Well, here's one way to think about, maybe to think about these images. We have all the gory details at the pixel level, and we have our continuum description, which is, this is the dog. And in between, in mesoscales in between, there are a whole bunch of correlational structures, presumably, that we can exploit in order to be able to make a transition or a connection between the input scale and the output scale, recognizing that that's a dog. Exactly what happens in the context of fluids, et cetera, where you have all this information, all these details about the molecular interactions, which don't get you any connections to the continuum behavior that you might care about. But instead, what's important is this middle scale, mesoscale correlational function strategy. So the explanation for this, I think, has to appeal to actual facts about the world, the scale invariance, and to the means by which deep neural nets identify functions that detect correlations that yield that scale invariance. So now, it's well known that the training of deep neural nets takes place using a variety of data sets. In the context of image recognition, these data sets include a bunch of things. MNIST, which is a large database of handwritten numbers, originally used in order to train machines to recognize zip codes, so they could fire a bunch of postal employees. Another database called Fashion MNIST, which is an MNIST-like database of labeled fashion images. And there's, I don't exactly know how people say this, CFAR10, it's a Canadian database. It's a very large database of labeled images from 10 classes, representing airplanes, birds, cars, deer, dogs, frogs, horses, ships, and trucks, a wide variety of categories. And then there's ImageNet, which is a huge database containing more than 14 million labeled images from more than 20,000 classes or categories. And there are lots of other databases that are at our disposal. And there have been empirical studies of the statistics of these data sets using the so-called theory of random matrices, random matrix theory. These involve the study of the eigenvalue spectra of the matrices, representing samples from the various data sets. And those are defined in this way, where D is the dimension of the image vector and M is the number of samples. This matrix, sigma sub M, is a covariance matrix. Basically, it's telling you how things covary, and it's also called a random matrix. So empirical investigation shows that the bulk of the eigenvalues for various data sets represent the correlational structure of different features among themselves. That's what I mean by covariance matrix. and that these decay as a power law, lambda sub I, eigenvalues proportional to I and then minus 1. And in this context, in pointing this out, Levy and Oz explicitly referenced Rudderman's scaling law that I introduced, that I started with. Remarkably, at least in my view, the various data sets that I mentioned earlier all exhibit the same power law behavior. And here's some plots that show that. So these are log plots. And what we have here is this purple plot here. That's for uncorrelated Gaussian data. You don't see any power law behavior in that. But all these other data sets, CFAR, fashion, MNIST, ImageNet, etc., they all exhibit the same scaling behavior. And we can say various things about the power, the exponent and the power. So the value of alpha reflects the strength of the correlation in the covariance matrices when you take a look at these different data sets. And I find this to be remarkable. By the way, I also thought that when I first read this, that scree plots was a typo. I think like they're screen plots, but no, it's a statistical term. And the reason they're called screen plots is because the shape of these things is actually supposed to represent the shape of scree fields. So for anybody who's done any mountaineering, it had to climb over scree fields. Okay, so the fact that the images of the world present themselves with certain statistical structure is, I want to say, critical to understanding how deep neural networks are actually able to generalize. So here I want to present some results of empirical studies on actual trained deep neural nets that have been trained on various data sets. So these and I'm taking this from a really nice paper, a very long paper on implicit self-regulation in deep neural networks, evidence from random matrix theory and implications for learning from Martin and Mahoney in 2018. So what they do is they look at a bunch of trained state-of-the-art neural nets and they try to analyze what's going on in the training process and what can they say. So they give evidence that this thing called the empirical spectral density, which is just a probability distribution of the eigenvalues of the correlation matrices, exhibits statistics from a random matrix theory universality class of so-called heavy-tailed distributions. These are power law distributions, and heavy tails are often marks of complex systems. So here's an aside. Heavy tail random variables have a relatively large probability of yielding a really large value in comparison to normal or Gaussian random variables that have exponentially bounded tails. So a random variable x is heavy-tailed if there's a positive parameter alpha, which is the probability that x is greater than value x is asymptotically proportional to x to the minus alpha. And compare that to a normal random variable, so it's like this, and you'll see that they're very different, or you can just look at this picture and see that. Right? Sorry about that. I got carried away. Okay, so Gaussian distributions tend to have exponentially bounded tails and don't therefore give much probability to outlier events, whereas fat tail, heavy tail distributions do. And it turns out that these scaling laws that we just pointed out in the various data sets have this heavy tail distribution. So Martin and Mahoney represent what they call the energy landscape or the optimization function of a typical deep neural net as L layers with activation functions H sub L, weight matrices per layer W sub L, and biases in this way. And what we really care about is they study the weight matrices at different layers during and after training on the various databases for a wide range of actual deep neural networks. And specifically, as I said, they analyzed the empirical spectral density, this density of eigenvalues of the correlation matrices associated with the particular layers in the deep neural nets. So what does random matrix theory do? Well, it kind of provides a law of large numbers like and central limit theorem like results, not for sums of random variables, but for matrices of random variables. And it yields unique results for both square and rectangular matrices. But in the context of deep neural networks, square matrices are relatively rare. Typically, the number of parameters n are much greater than the number of examples that they're trained on. And a lot of work, sort of traditionally in random matrix theory, focused on a class of matrices that are members of the universality class of Gaussian distributions. So as an aside, this stuff played a big role in my some of the things I used to think about when I thought about chaos in quantum mechanics, because there are different universality classes characterizing the distribution of eigenvalues for quantum systems whose classical counterparts are integrable. They exhibit Poisson-like behavior. And for those which are non-integrable or chaotic, they exhibit different universality classes, Gaussian orthogonal distributions. But the correlation matrices in this universality class of Gaussian distributions have a particular form. In this situation, the spectral density functions defined here, right, with a certain aspect ratio fixed, and the limit as the number of parameters goes to infinity, take the form of so-called Marchenko-Pastur statistics. And that's given here. So what does this mean? Well, what it means is that the analog of a Gaussian distribution, or ordinary statistics of random variables, the analog of that in the context of random matrix theory, where you're dealing with matrices, is this Marchenko-Pastur distribution. And this is sort of what it looks like. So if I were showing you various Gaussians, you'd all see, you'd know what you were looking at. But in this case, these are the different Marchenko-Pastur distributions, MP distributions for this eigenvalue spectrum here with different aspect ratios and over M with fixed variances. And note that there's a lower lambda minus and a lambda plus, and those change as you change these various values. So, as I said, these in effect are the matrix analogs of various Gaussian normal probability distributions. So Martin and Mahoney empirically investigate the statistics of the weight matrices for fully connected layers in a number of trained state-of-the-art deep neural nets. They observe, quote, profound deviations from the traditional MP-based, Marchenko-Pastur-based random matrix theory. They find that the DNNs are reminiscent of strongly correlated disordered systems that exhibit heavy-tailed behavior. That's sort of giving a little bit of an idea of what heavy-tailed behavior is. Most importantly, they argue that the training process for these deep neural nets self-engineers a form of implicit self-regulation in the training model. Right? There's no need in this situation to introduce any kind of ridge regression or other sorts of regularization techniques in order to make sure you're not, because that's the main thing. There's so many parameters in these things that they overfit, they can memorize the data, yet they still generalize well. And so when on data that they haven't seen, and so what we're trying to do is understand that. And I'm trying to give you a story about maybe that's where that might come from. Okay, so here is a taxonomy of some trained models, and you can think of this as each of these instances going from left to right, top to bottom, are gotten by looking at the covariance matrices and the distribution of the eigenvalues in those matrices at different stages of training. So the first one here, where there's a random like empirical spectrum density, that's a really good fit to the Marchenko-Pastur, the random. So that's what you would see when you initialize the DNN with random parameters. Right? But as it trains, they identify a bunch of different kind of universality classes. But what we want to, but when they're fully trained, basically the idea is that the Marchenko, the NP fit gets worse and worse and worse, and ultimately in the fully connected layers near the top of the neural nets, near the output, these eigenvalue distributions take on the form of heavy-tailed distributions. And they see this over and over again with different neural nets of different types trained on different data sets. So the figure that I just showed you explicitly exhibits the evolution of the statistics of these empirical spectral densities for the correlation matrices associated with various layers in the gene. These empirical spectral densities evolve under training, where we use stochastic gradient descent or some kind of back propagation algorithm to adjust the weights upon learning that, oh, I misclassified this image as a dog. I have to go back and slowly adjust all the weights. That's how these things learn. But these empirical spectral densities evolve from random-like distributions with good Marchenko-Pastur fit, as I showed you, associated with random initialization at the start of training, to heavy-tailed distributions that correspond to strong correlations for the weight layers at the end of the training, when the machines have sort of learned and are performing well. So the idea is that one can model these empirical spectral density distributions of trained neural nets with heavy tail distributions using random matrices. And Martin and Mahoney note that for deep neural nets, these correlations arise in the weight matrices during backdrop training, that is stochastic gradient descent training, at least when training on good data. And another way of putting it is that the weight matrices learn the correlations in the data. So it seems to me that if true, and given the robust statistical power law behavior of the various data sets, might help to explain some of the remarkable successes of deep neural nets. They're learning the statistics and taking on the statistics in their weight matrices of the data sets upon which they're being trained. All right, so I can conclude the training. Faster, maybe I just don't have enough stuff to say. So what I have hoped to motivate is the idea that the success of deep neural nets on certain tasks can be understood in terms of their ability to discover correlational structures that are present in real world data. And it's remarkable, at least to me, that the various data sets used to train the DNNs all exhibit scaling behavior similar to one another and similar to the behavior that Batterman discovered in his investigations of the statistics of natural images. And one way to think about this, what I've been thinking about for 20-something years, is an analogy with the universal behavior of critical phenomena. Right? So here's a picture that probably some of you have seen before. Each one of these points on here are different fluids. Neon, argon, krypton, xenon, nitrogen, oxygen, carbon monoxide, and methane. And these points here. So this is called a coexistence curve. Because if I'm near a sort of boiling point for a fluid, there's going to be a coexistence of liquid phase and a vapor phase. Just think of water in your tea kettle, right? And as I approach the critical temperature, the difference between the density of the vapor phase and the density of the liquid phase vanishes, and it vanishes at the critical temperature and at the critical density. That is an order parameter, and the shape of this curve here, upon which all this data collapses, is the same for all these systems. Right? They're plotted in reduced coordinates. So all I'm doing when I go up this T over TC axis is saying I'm closer and closer to criticality, to the critical temperature, regardless of what the actual critical temperature is for any of these systems. They're all different. So this is a remarkable bit of universal behavior, or multiply realized behavior by different systems, for which the explanation for which Ken Wilson won the Nobel Prize, which should have been shared with Michael Fisher. So the thing is that if I were to plot this picture on a log-log plot, like the scree plots that we saw for the data sets, it would be a line too. So that's, you have power law behavior when you have log-log plots that are linear. So if we were to go back and look at the various data sets and ask what's going on for those various data sets, we'd see that they would all have a similar kind of plot like this. So that's how I like to think about it. So just as in this figure from Guggenheim, the different data sets upon which the DNNs get trained all exhibit the same scaling law behavior. And that's true despite having widely different details in their fundamental pixel scales, despite being data sets of very different images. So a lot of the literature on deep neural nets, specifically deep convolution neural nets, which are the ones that typically are involved in image recognition, focus on the ability to serve as feature detectors, features that are present in the images that they receive as input. They're said sometimes to detect low-level features like edges at early levels in the architecture. Then in deeper layers, they manage to combine lower-level features into more abstract features that enable them to recognize or learn, perhaps, that certain images are images of dogs. So I think that this talk of feature detection is somewhat misleading, since it seems to imply that deep neural nets are recognizing certain aspects of semantic categories. I'll go back so you can take the picture. Remember that Renormalization analysis explicitly avoided semantic understandings of the objects that appear in the images. So rather than identifying objects and images semantically, as the term feature detection sometimes suggests, and I think a number of people actually talk this way, Cameron Buckner for one, in certain papers. Batterman argues that we should think of the objects as statistically defined. And in doing that, he was led to determine the probabilities that two pixels separated by some angular distance x belong to the same object. And as he says, the notion of statistically correlated and uncorrelated regions within images corresponding to objects, within images corresponding to objects, provides a simple, robust path to scale invariance, as long as the objects appear in all sizes according to a power law distribution. So this is an implementation of that mesoscale correlational methodology that I think is actually quite ubiquitous in dense matter physics and even in materials science. Rudderman's conclusion, recall, was that the scaling of inter-object probability follows directly from the scaling of apparent object sizes. In images of real world, its apparent size in degrees depends upon an object's actual size, as well as its actual distance from the observer. The overall distribution of apparent object size is thus a function of the distributions of the object sizes and that of the distances. So the real world structure is important. The real world mesoscale structure determines the correlational structure among the pixels in the images. And ultimately, I think this is what allows deep neural nets to correctly characterize images. There's a lot more to be said, and there's a lot more I need to learn about it. And finally, there is evidence that deep neural nets that have been trained on one data set require considerably less training to become image classifiers on data sets that they haven't seen. You might say, that's really weird. Why? They haven't seen. After all, the data sets are of very different images, right? But maybe that's because they've already achieved a kind of alignment with the so-called ground truth function, the robust power law scaling behavior that's present in all of those data sets. And so maybe it shouldn't be so surprising that the deep neural net supports so well to the other data sets. They already have the weight parameter structure that corresponds to the statistics that are already in the new data sets, since the statistics are all essentially characterized by the same values. Thanks.
As is tradition, we'll take a quick break and we'll resume at 5 to the hour.